one?
This mic is the right.
Oh, that's fine. Good.
Oh.
Okay, I can just speak up. People will hear.
Okay.
So hi everyone. I have the pleasure of introducing the speaker today. We have Cynthia Rudin here for our special edition seminar, the Blackwell seminar this year. So I would like to first say a few words about the seminar series, and then about our speaker, and then we'll get started. So the Blackwell seminar was established in 2020 to honor the contributions of David Blackwell to mathematical statistics, game theory, probability theory, and information theory. It focuses the seminar on the topics at the interface between statistics and equity issues such as racial disparities, social justice, and ethics. And speakers are invited based on their contributions to these areas. And takes place once a year in the fall. The speakers are selected in the spring, but mostly by students who are members of our Diversity, Inclusion, Community, and Equity Committee, or DICE. I am currently chairing this committee. Please join us. It's a great way to participate in shaping the department processes, and also in getting to choose our speaker for next year. So we're very happy that Cynthia accepted our invitation and give this talk. I'm going to give a talk on simpler machine learning models for a complicated world. And just a little bit about Cynthia. So Cynthia is the Gilbert, Louis, and Edward Lerman Distinguished Professor at the Department of Computer Science. She directs the Interpretable Machine Learning Lab, and her goal is to design predictive models that people can understand. Her lab applies machine learning in many areas, such as healthcare, criminal justice, and energy reliability. She holds degrees from the University of Buffalo and Princeton, and is the recipient of the 2022 Squirrel AI Award for Artificial Intelligence for the Benefit of Humanity from the Association for the Advancement of Artificial Intelligence. She also received the 2022 Guggenheim Fellowship and is a fellow of the American Statistical Association, the Institute for Mathematical Statistics, and the Association for the Advancement of Artificial Intelligence. So I hope you will all join me in welcoming Cynthia. Cynthia has asked that we keep your questions until the end, but other than that, I hope you all enjoy, and welcome.
Thank you. All right. Normally, I usually welcome questions, right? I don't want to discourage them. I'm going to stick around afterwards to discuss any questions you have, but there's something special at the end that I think the audience will like a lot more than questions for this particular talk. So if you could keep the questions to short, clarifying questions, then we'll all get a reward at the end. Okay. So my lab at Duke is called the Interpretable Machine Learning Lab, and one of my most important goals is to create predictive models, so machine learning models, that are small enough to fit on an index card, yet are as accurate as the best black box models like deep neural networks. And you're probably thinking, is this for real? Like, can you actually do this? Because this would mean a lot for trustworthy and fair machine learning if you could do this. And the answer is yes, we can totally do this for a lot of really important circumstances, a lot of really important problems. And we think we know like when you can do it, when this happens. You can't do it for computer vision, you can't do it for language, but you can do it for many, many other problems. So let me give you an example. So a few years ago, there was a competition sponsored by FICO, which is the major credit scoring agency in the United States, as well as Google, MIT, Oxford, Berkeley, and others. It was called the Explainable Machine Learning Challenge. And they gave everybody a data set about loan decisions, and they told everyone to create a black box predictive model and explain it, because they didn't think that it was possible to create an interpretable model with the accuracy of a black box model for such a complicated data set. And several years after the competition ended, my team figured out that there are accurate interpretable models. You just have to look for them carefully. So let me tell you a little about the data set. It's got about 10,000 loan applicants from a particularly difficult subpopulation. The goal is to use credit history to predict whether someone's going to default on a loan. At the time, which was 6 years ago, nobody produced a tiny little model that was as accurate as a black box, like maybe that boosted decision tree model there. But 4 years later, we produced the first small models that performed as well as the black boxes. And because we had these new machine learning algorithms, these new powerful machine learning algorithms that could actually do this. And because the models fit on an index card, they also fit on a PowerPoint slide, so I can show them to you. So the first model that I'm going to show you was produced by the fast sparse algorithm, which creates sparse generalized additive models. And this is work that was done with Jiacheng Liu, Chudi Zhang, and Margot Seltzer. And this method is an extremely fast coordinate descent method that minimizes the exponential loss with L0 regularization. And it has analytical solutions for the step size at each step, which makes it run really, really fast. So let me show you the model here. So this is the whole fast sparse model for the FICO data set right there. You just get a score for each of the variables and you add them up. And that translates into a risk of default unalone. And we can take a look at some of these things. So months since oldest trade open. So if your oldest trade is recent, you get more risk points. And if the number of satisfactory trades is only like 10 or less than 10, then you get more risk points. And external risk estimate, this is like a particularly sensitive feature between about values 60 to 80, okay? So what's really shocking about this model its statistics are both AUC and accuracy are extremely similar to the boosted decision tree model and the best neural network that you can get on this data set. But what's really cool about this model, besides its simplicity and describing the complicated this data set, is that we created it in under 4 seconds. Okay, so that's how fast this algorithm runs on average. It takes 4 seconds on this data set. And it used to be that finding high quality interpretable models was so difficult that you couldn't do it at all. But now we can do it in just a few seconds. So let me show you a different type of predictive model for the same data set. This one's going to be a sparse decision tree. It's created by the GHOST algorithm. So GHOST is generalized optimal sparse decision trees. And it was developed over the course of a decade. I've just put pictures up of some of the people who've been working on GHOST. GHOST is very fast. It's orders of magnitude faster than the previous approaches for producing provably optimal sparse decision trees. And it's so much better than like CART or C4.5 that like greedily split the tree from the top down. This algorithm fully optimizes the trees. So let me show you a decision tree for the FICO data set. So here it says, if the external risk estimate is too high or too low, then you've got a prediction. Otherwise, you got to ask these more subtle questions like, months since most recent inquiry excluding the last 7 days, is it less than 0.5? Is it 0 or above 0, like that? So I just want to point out how difficult this model is to create, right? The algorithm has to figure out all kinds of stuff. It has to figure out all these thresholds here, like 70.5 and 78 block. It has to figure out where to put each of the variables, the size and the shape of the tree. All that stuff has to be figured out by the algorithm. And it's computationally hard to do this. It's NP hard, no polynomial time approximation. And yet the optimal tree was created by GHOST in 8.1 seconds. All right. This is actually the same tree that's on the previous slide. It's just done in a more artistic way. This is done by an artist friend of Margot's. And it's like this kind of like powerful predictive model kind of growing in nature. I find interpretable models much more natural than black box models. Like black box models might be kind of like snarls of branches or something. Okay, so what I've explained to you so far is that even on competition data sets, we can find interpretable models that are as accurate as the best black box models. Okay, so if people aren't using interpretable models, what are they using? Black box models. Okay, and these are models that are either too difficult for a human to understand or they're proprietary, which means their computations are hidden. So what's wrong with using black box models? Well, they are difficult to use in practice. I have an example here from criminal justice where a typographical error in someone's risk score, their criminal history features there was an error in there, and that caused them to be denied parole. So, this is not the way we want our criminal justice system to work. Typos should not be making decisions. People spending a year in prison because of a typo is an embarrassment. Black box models are difficult to explain. If I get denied a loan and I can't buy a house, I actually want to know why. I don't want some crappy explanation of a black box. and black box models are difficult to troubleshoot. Healthcare is a huge can of worms here. I have an article there which is about a black box model that was approved by the Food and Drug Administration for use, and then they launched it into practice. This is for detecting intracranial hemorrhages, so, you know, blood bleeds in your brain, and the model didn't work, and no one knows why. All right, so black box models in healthcare deserve their own slide here because they cause so many issues. Like, so you often have this situation where the model is right, but for the wrong reasons because of some correlation, and then when you go to use it in practice, it messes up. You know, you don't really want to leave high stakes decisions to a model that doesn't really understand the whole situation. You've got all these issues with troubleshooting. You just can't second guess the reasoning process of a black box because you don't know what it is, right? All these things, all these questions becomes difficult when you use a black box. And then you have issues of responsibility or accountability, right? Who's making the decision here, the human or the machine? So my point is that black box models turn what would be computer-aided decisions into automated decisions. And so I think black box models really shouldn't be used in many healthcare decisions if at all possible. Okay, so if black boxes are bad, why do people keep using them? Well, I think there are at least 3 reasons. And the first one is that people don't actually believe that interpretable models can be as accurate as black box models. It doesn't matter how many examples you give them. When a new problem comes along, they still go, oh, this is probably something that needs a black box. Now, I can understand this for domains that really benefit from neural networks like computer vision or, you know, speech. But if it's in a domain that's never benefited from black boxes, neural networks, people still say this. And the second reason is that people really like black boxes. You can sell a black box, right? Black boxes can be someone's secret sauce. You know, you can't really sell somebody something that fits on an index card, right? You get to sell the mechanism to collect all the data from the patients and to combine it behind the scenes and so on. And then the third reason is that interpretable models, well, I'm going to try to convince you that were hard to create, right? They were hard to create because now we have these new algorithms that can do it. Now, I'm not sure if I can handle the politics on the secret sauce bit, but I can definitely help with the first one and the third one. So I'm going to just keep discussing the third one, okay? So I think a key reason why interpretable models are hard to create has to do with the interaction bottleneck that arises when people realize that interpretable models have interpretable flaws and they need to fix them. So let's say that a doctor is using data to produce an interpretable model, and the doctor looks at it, which is now possible because it's interpretable. And then they see that the model doesn't align with what they know about medicine. So what do? Right? The machine learning algorithm gave them this model, right? And so the doctor's stuck. Right? Even if there were hundreds of millions of equally accurate models, the algorithm returned only one of them. Right? These models, they're all equally accurate with respect to the data, right? With the data you've got, there's literally no way to tell those models apart. They're all equally good, but the algorithm returns only one. Right? The only way to tell the difference is with domain knowledge, with outside knowledge, with prior knowledge. But there's no easy way to put the domain knowledge into the algorithm, and doctors don't always know the domain knowledge in advance. And this is a real problem, that there's really no feedback loop, natural feedback loop in machine learning, right? Machine learning algorithms return only one model at a time, so in interacting with these algorithms, machine learning algorithms, is a problem that the standard machine learning framework is just not equipped to deal with. So we need an entirely new paradigm for machine learning at this point, right? Machine learning is just totally broken here. All right, so my collaborators and I decided that the standard machine learning framework had to go. So we proposed a new paradigm for machine learning, and it's something that's more human-facing than the standard machine learning, which is to hand the user, you know, all of the good models from a given function class, not just one model, right? All of them. and then let them choose which model they want so they can pick something that agrees not just with the data, but also with their domain knowledge, so that they might actually want to use that model. And we call this set of good models the Rashomon set. And now I want to point out that doing this is extremely technically difficult, right? Finding even one optimal sparse model is NP hard, right? It's provably hard computationally. But now I'm saying that we have to find all of these good sparse models. We have to store all of them, even if there are hundreds of millions of them. And we have to visualize them so that the users can choose from them. So it's not easy from a technical perspective, but it's extremely useful in practice. And it changes the whole notion of machine learning from just optimization to also including enumeration and storage of the Rashomon set and also visualization of it. So I want to show you an example because we now have the first algorithms that compute the whole Rashomon set for non-trivial function classes. So the first one that we created was for sparse decision trees. And this, this is an example of a ghost tree on a criminal justice data set. This is a criminal recidivism data set. And it's just one tree here. And the algorithm in the new paradigm is called tree farms, this algorithm. And it finds not just one tree, but it finds all of the good sparse trees for the whole data set. And it works for reasonably sized data sets, and it displays them in an interface called TimberTrek. So I'm going to just click here, and it's going to bring up TimberTrek on my screen here. So I just went to, this is a publicly available website, just public website that anybody could have done this at the same time I did. But anyway, what it's showing here are all of the trees for this data set in gray. And then what you can do with the Rashomon set, if you want to find just trees the blue features are criminal history features. And so if you want to, say, start with number of prior crimes greater than 3, you can click the number of prior crimes greater than 3 button, and it'll limit you just to trees where that's the top split. And if you find a tree that you like, you can click it, and then maybe you can put a little heart on it. You could put a little note on it that says, you know, that says, like, I like this tree, or whatever you want there. And then you can also display the tree by how many points go down the different the branches. So here about a quarter of the data points are going this way, and then 3/4 are going that way. And so you can really get a sense of what's going on in that tree. And then, you know, you can also limit further if you want to trees that just have certain branches at the top. And if you don't like your choices, then you can just click back out and get back out. There's also, the problem is I can't navigate here because I'm at a weird angle, but there are filters here. So if you wanted to filter just by, like, let's say that you didn't want trees that used the sex equals female variable, then you can click a button and it just gets rid of all of those trees. And you can, the nice thing about having the whole Rashomon set there is that you can filter it by, like, if you have a fairness constraint that you want to put in, or if you have like a monotonicity constraint that you wanted to include, all you have to do is filter the Rashomon set, and so it's instantaneous. You no longer have to solve an optimization problem that you would normally have to solve if you didn't have the whole Rashomon set at your fingertips. Okay, so the nice thing about this approach, or nice things about this approach, are that there's no more interaction bottleneck. It really makes the feedback loop to humans essentially instantaneous. It's like thumbing through an encyclopedia to find your model rather than trying to reformulate the problem over and over again with different constraints or different priors or something like that. And it also allows you to incorporate constraints essentially for free. Like I said, it used to be hard to put the fairness and monotonicity constraints in there because you'd have to solve a really hard optimization problem with those extra constraints. But now, since you have all of the good models, you just filter. And so that's like a single loop over the Rashomon set. It's really easy. So I hope you're starting to see the value in this new paradigm. It's a lot more computation up front, but it completely annihilates the interaction bottleneck and constraint handling. Okay, so let me tell you a little bit of how it works. I'm not going to go into detail since it's really complicated. The first step in the tree farms algorithm is to run the ghost algorithm. And ghost finds a sparse tree that minimizes the subjective function, which is a combination of the misclassification error and a constant times the number of leaves. Okay, and you really do want this term in there. Like, even if you have a depth constraint, you really want this soft constraint in there, the regularization on the leaves, because if you don't have that, then it'll fill in the tree to the depth that you limited to. So you really want to keep the tree sparse, so you need to keep that there. It'll have, like, the tree would have unnecessary splits if you didn't have that. So you run Ghost, you get the minimizer, and then you want all trees within epsilon of that minimizer. That's the Rashomon set, and then Tree Farms is going to go find that. And the key ingredients for Tree Farms are a dynamic programming formulation, theorems that reduce the size of the search space so that it's manageable to actually search it. And what happens is that these theorems create dead ends for the dynamic programming all the time. So when you're doing the dynamic programming, you reach subproblems, and the theorem tells you that you're at a dead end. So you don't actually have to search that whole part of the space because you know that no element of the Rashomon set is there. So the theorems just reduce the search space like a huge amount. And then the third element is what we call the model set representation, which is a data structure that allows us to efficiently store hundreds and millions of trees. And it stores them in an implicit way so that you're not actually, you can enumerate them still, but what you're storing is like parts of trees that can combine with other parts of trees to form the whole Rashomon set. So you're never actually, you're not storing like each tree separately. It's like these parts of trees can combine with these parts of trees. So it's, you know, it's combinatorially smaller than actually storing the Rashomon set one by one. Okay. So you might be wondering if we need something as fancy as Tree Farms, right? Especially if you like to sample, if you're Bayesian perhaps, like you might say, oh, can we just get the Rashomon set by just sampling lots of trees? And so we asked, do other methods produce all almost optimal models? And as it turns out, they do not. So just to show you an example, on the Monk 2 dataset, Tree Farms finished its computations of the Rashomon set in 46 seconds. So we ran a bunch of other things for 46 seconds to see what would happen. So in 46 seconds on the Monk 2 dataset, we ran Bayesian additive regression trees. It constructed 488 unique trees. How many of them were in the Rashomon set? Well, only 3. Random forest created over 20,000 unique trees. 0 of them were in the Rashomon set. Cart on random bootstraps of the data created over 20,000 unique trees. Only 7 of them were in the Rashomon set. And then we compare that to Tree Farms, which provably provides the whole Rashomon set, and it gives us over 105 million unique trees. So if we would have no idea the Rashomon set was that big if we didn't have Tree Farms. And we also get similar results on other data sets. Okay, so I'm going to switch model classes for a minute. I'm going to switch over to risk scores. So risks. Yeah, sure.
So when you're counting these, if you have a continuous feature, are you counting all split points? Are they all discretized somehow?
Yeah, so you take every possible split point. So every 2 values in the data set, you create a possible split point there, and then you use all of those split points. Yeah, that's right. So for example, for ages, you would put a split between every age. Like if there was somebody 21 and 22 in the data set, you'd put a split at 21.5. If there was nobody who's 22 years old, but somebody 21 and 23, you put a split at 22. Yeah. And you can, if you ask me afterward, I can tell you other ways to reduce that number, because it gets to be a large number. So what you can do is, like, you can run a black box like boosted decision trees that gets very high accuracy, and you can just use the split points from that. You lose the guarantee of optimality, but what you gain is a guarantee of getting at least as good as the black box. Yeah. Okay, cool. All right, great. So I'm going to switch model classes over to risk scores for a minute. So risk scores, our latest method for risk scores is called faster risk. Faster risk sounds like asterisk, which is why there's a giant asterisk back there. So risk scores are sparse generalized additive models with integer coefficients. Scoring systems are very simple model forms. You just add up the points and get the risks from the table, but these things are notoriously hard to construct because you get both sparsity and integer constraints, which makes it kind of painfully hard. So this is faster risks result on FICO. This thing loses a little bit of accuracy compared to FastSparse and Ghost because it's just so constrained. But it's really crazy simple and pretty. And the algorithm's pretty fast. This one gave us the result in 13 seconds. I'm going to show you another one just to kind of get you the sense of what these risk scores are. So we've been using it to make mortality risk scores from the giant MIMIC3 data set, which is a large public ICU data set. Physicians use these kind of models a lot. So I'm going to make this bigger on the next slide and just zoom in again here. So this is showing you that if your maximum temperature within the last, couple hours is abnormal, like if it's too low or too high, you get some risk points. If your pH is too high or too low, you get risk points. Urine output, blah, blah. Okay, so then you get total number of points. It adds up and produces a risk using this table at the top. Okay, so the algorithm, FasterRisk, produces a bunch of models from the Rashomon set. And so what we have been doing recently, and it's the first time I get a chance to show this in a talk because it's really quite recent, we designed something called Riskamon. And what it does, I'll just zoom in a little bit so you can see it. It's showing you like the models here on this axis. So these are just the model numbers. And so you get -3 points for circumscribed margin. This is a breast cancer data set. 2 points for irregular shape, right? So that's how, this is the whole risk score. And then here's another risk score and another one. And right now it's showing one of them at the bottom here. This is kind of zooming into one of those risk scores. And it's telling you sort of, if you get how many points you get, what is the translation into risk? And then this is the risk score itself. And you could say, well, I don't really like this model because speculated margin only gets 1 point, and I think speculated margin should get more points. So what you can do is take a look at all of the models here and say, I want a model with speculated margin getting 3 points. And then it'll place that model's model card down at the bottom too, and you can see what the translation from scores to risks is there. Okay, cool. So you now have seen 2 views of the Rashomon set here. Okay, so we've at least made a lot of headway in dealing with this third issue that interpretable models were hard to create. But so now that we established the Rashomon set paradigm and dealt with the third point, I want to switch gears to talk about the first issue, which is that this idea of belief, that people don't believe that black box model or that interpretable models can be as accurate as black box models. So what in the world would convince these people? I mean, I figure, look, I've been presenting examples, for a decade on real data sets about the existence of interpretable models, and they didn't believe them then, and they don't believe them now. Okay, so if they don't believe the evidence from data sets, I said, maybe I could try to prove, do it with a mathematical proof, okay? So the goal became to sort of prove that interpretable models are likely to exist for data sets with specific characteristics, right? So that way, by knowing something about how your data is generated, then you should be able to know kind of like right then and there, like before running any machine learning algorithms, whether this is going to work, whether you can get an interpretable model that's accurate. So in order to get us into the right frame of mind for this, I just want to talk about the universe of supervised learning problems, okay? So there are really 2 different worlds of machine learning based on the kind of data that you're working on. Most people think these 2 types of problems are the same, but they are not. They are fundamentally different, which is probably why people are getting confused. So the field of machine learning has mostly focused on what I'm calling raw data problems, like vision and speech and language. And here, you can make really complex models, like really deep neural networks, and they actually generalize between the training set and the test set. But for tabular data, which are the kinds of models that I've been showing you, if you use a really complex model, it's not going to work. It's just going to overfit. And you're not going to see the benefit of the extra complexity. Okay, now there's one important difference between these 2 problem types, which is that the raw data problems have certain outcomes, like outcomes that are certain. So for image recognition, for instance, an image either contains a chair or it doesn't. So if you're identifying chairs and images, you can do that with over 99% accuracy. Okay, whereas most data-driven problems in the world, like these ones, are not like that. So like the FICO data. Or for example, let's say you got two medical patients with almost identical medical records. One could have a heart attack next year and the other one might not. And we would think that that's completely realistic, right? So, deep learning really hasn't had an impact in these kinds of problems, and I believe I understand why it can't. Right? It's not about whether we have the right algorithms, it's just something inherent about these problems. So that's what I'm going to tell you about. So here's a simple visual example in 2 dimensions. This is a clean data set where you can fit the data perfectly and everything's fine, but as soon as you introduce a little bit of unpredictability, like some label noise here, then boom, you overfit. All right, so Leslie Semenova, Ron Parr, Harry Chen, and Zach Boner and I have written these 3 papers. One of them was just accepted last week. But anyway, these 3 papers that together aim to give some semblance of the beginning of a mathematical proof that noise actually causes the whole problem. Like well, it's not the problem, the whole thing, right? Noise is what leads to large Rashomon sets. Large Rashomon sets lead to the existence of interpretable models. Okay, so I'm going to show you just a picture at the bottom so you can understand what I mean. So here you can see that this noisy data set has a pretty large Rashomon set, and the clean data set has like a smaller Rashomon set. And the theory is a little bit hard to understand if you're not a machine learning expert. So I'm going to try to explain it, but to be honest, it really doesn't matter if you understand every step of the proof outline that I'm going to do, as long as you come away knowing that there's some sort of proof out there. Okay. All right, so the first step in this path, it's a path from noise to the existence of simpler models. So the first step in the path is that noise in the world leads to increased variance of the outcomes and increased variance of the error, okay? So I used to think that if you took a clean data set and you added a bit of uniform random label flipping noise to it, then the predictive error of all the functions would just go up, right? All the models would just the losses would just get higher. And the bad models would still be bad, and the good models would still be good, and the Rashomon set would stay the same. But yeah, that doesn't seem to be the case, and in fact, it's totally false. Okay, so when you add noise, the variance of the labels increase, and then that means the variance in the error increases because the labels go into the error function, and so the error gets harder to estimate. So you can't see what you're doing, right? You just can't estimate anything very well. So all of a sudden, you're just like in this cloud of uncertainty smog, okay? So you just can't see it. And we've been able to prove that this happens for special circumstances. So for instance, we've proved it for uniform label flipping noise. We've proved it for when labels are flipped with a probability that depends on X. And then margin noise, which is where you basically smush 2 Gaussians together. And all of them have increased variance of the error with the label noise. And then second, higher error variance, like this extra variance in the error, leads to worse generalization between training and test. And this you can see based on a theorem the theorem is based on Bernstein's inequality. Generalization bounds, they're not perfect, but they tend to have the important quantities in them. So in this case, it's the variance of the error. And this is, Bernstein's inequality is tighter than Hoeffding's inequality, which is what most of the generalization bounds are typically using. So we actually think it's pretty tight. So what I'm saying is that the loss variance is an important quantity in generalization, and it is increasing. So anyway, model doesn't generalize. But the analyst is not stupid. They're not just going to use an overfitted model, right? The analyst can see this happening because they're using a validation set. So the analyst sees that they're overfitting, and they compensate by simplifying the function class. So I could stop here because now I have a simpler function class, but let me keep going because something bigger happens too. So anyway, the analyst simplifies the class so that they can generalize between the training and the test set. But the new smaller function class has a large Rashomon ratio, which is the fraction of good models. Okay, so the fraction of good models goes up. Okay, so why is that? Okay. So as you go to more complex function classes, you have more good models than you did before, because you have, you made your function class bigger, so you have more good models, right? Because you have more models. Great, so the thing is, the number of total models in the function class, so you have more good models, but you have a lot more models, and that number goes up really, really fast. So for these, all of a sudden, for these more complicated function classes, you've got tons and tons of bad models, and the number of good models is just tiny in comparison. And this happens because each good model that's in the simpler function class gives rise to a few good models, but mostly bad models. And the bad models rarely give rise to good models. So let me show you an example here. So let's say, you're working with the smaller function classes, kind of small trees, and the larger function class are deeper trees. And here, if you grow these small models, if you have good models, they grow into large good models, but they often grow into large bad models. They do that more often. Whereas if you start with a bad model, it doesn't grow into a good model all that often. So if you kind of grow it, you generally grow a bad model. Okay, so we actually have two proofs for this. We have one for decision trees, showing that the Rashomon ratio is larger for decision trees of smaller depth. Okay, so Rashomon ratio is larger for decision trees of smaller depth. And we also have a theorem for ridge regression, that the Rashomon ratio increases with noise for ridge regression. Okay, so now we've got a large fraction of the function class being good models. Maybe, it's not half or anything. It's usually smaller than 1%, but hopefully you get the idea. Yeah?
The amount of error that defines a set, is that kept the same?
Yeah,
a simple model?
Kept the same. Okay, so we're going to do this covering argument. And this set is large. The Rashomon set's large. It's large enough to contain a ball. And then what we do is we say there's an even simpler function class of models that serves as a good cover for the space. So you could think of like shallow trees covering the space of deeper trees, or like the shallow trees kind of represent the space of deeper trees. Like for each deeper tree, there's a shallow tree nearby. Okay. And from there, since there is this big ball of good models, then you have at least one simpler model in it, right? One of these green dots is in this ball that's in this Rashomon set. And so you can have a model that's simpler and also good. And so by this argument, you can get these quite simple models that perform well. And so that's the last step, which is that if you have a large Rashomon ratio, simpler models are likely to exist by this covering argument. Okay, so that's the kind of proof outline. And one nice thing about all this mathematics is that the practitioner never needs to know how much noise is present for this to work. It just works. Okay, they'll just find simpler models automatically. They don't even need to know how much noise there is. And then in the paper that was just accepted last week, we've been trying kind of a more direct approach to get to simpler models, which is to prove that noise in the data acts as implicit regularization, which is, so that's the focus of this paper, that like when you have noise, that translates directly, it's equivalent to having more soft regularization. Okay, so I've told you now about the Rashomon set theory, and the implications for this theory are pretty intense. So the implication is that optimizing for simplicity won't sacrifice accuracy for a vast set of problems. It's any problem where there's noise and where you can't predict perfectly. So you can get a sense just by knowing one thing about how the data are generated, whether or not simple yet accurate models are likely to exist. And so if I'm right, this has huge implications for a lot of high stakes decisions that are made using data in our society that deeply affect people's lives. So that includes criminal justice decisions that determine people's freedom, for loan decisions that determine someone's ability to purchase a home, or for medical decisions that determine, life or death. Because if I'm right, then for none of these problems can we really justify black box models. For none of them. It's not like we didn't know this already. I mean, so for instance, now interpretable AI models also have a precedent in high-stakes healthcare decisions. This model, for example, is the 2 helps 2B score, which predicts seizure risk in critically ill patients. It is the only AI model used in critical care brain monitoring, and it was developed by our lab. Let's talk about criminal justice. Do we need black box models there? Well, my first paper on this was in 2017, so I've been studying this topic for maybe 9 years, and tiny little models do just fine for criminal recidivism prediction, even on data sets that consist of over 40,000 people. So I don't see any good reason why we should allow black box models in the determination of someone's freedom. And for loan decisions, I already showed you models built on the FICO dataset. Both were built in under 10 seconds, and they're about equally accurate to black box models like boosted decision trees and neural networks. If the major credit scoring agency in the United States provides data that they don't think can be handled by interpretable models, and they're wrong, think how many other people are wrong about this. Okay, so far I've said that even on competition data sets, we find interpretable models. I've shown you the Rashomon set paradigm, where you find whole Rashomon sets and not single models. This solves the interaction bottleneck. Constraint handling is now easy. And then I've showed you our attempt at a mathematical proof, which is this path to simpler models that starts with noise, right? It's like a proof that simpler models exist. And the fact that it has huge implications for criminal justice and loan decisions and other high-stakes decisions. Okay, so where do we go from here? Or at least where do I go from here? So, well, I think one thing these ideas could help with is regulation. So I think no black box model should be used for high-stakes decisions unless it's not possible to create an equally accurate interpretable model. And we know that's not very likely to happen for problems with noise, with uncertain outcomes. I think performance comparisons between models should be done in practice, not on static data sets, because we should be considering the whole system and not just the predictions. Like, we want to include the ability to troubleshoot the model as part of the evaluation. And that'll really show you the advantage of, using a model that people understand, right? Because they can troubleshoot it. And no stupid explanations of black box models. We don't just want to know which variable is important. We should be able to demand to know exactly what went into that decision that determined that important thing about my life. But regulation is taking a long time. I'm trying to help. I spend a lot of time volunteering on a government committee that makes recommendations to the White House. So I'm trying, but it's challenging. And in the meantime, I'm not waiting around. I'm building a lot of tools beyond what we've discussed. So changing topics, about half my lab works on interpretable neural networks and applications to healthcare, specifically mammography, neurology, and heart monitoring with wearable devices. So I got a lot going on. That's another talk for another day. One thing I really want to mention, though, is our work on dimension reduction for data visualization. This stuff is really useful. It allows you to project high-dimensional data to 2D to see what's going on. This example is with the Mammoth data set. This is a 3D data set. I'm going to try and reduce it to 2 dimensions. So it's like taking the mammoth and like crushing it onto the page like a leaf between 2 pieces of paper. And so if you try to do this with older methods like Tisney, it doesn't really work. It just dismembered the mammoth and ran it over with a steamroller. And it doesn't matter what parameters you set on the method, it always gives you garbage. This is UMAP, which is supposed to be an improvement. Still looks like a chicken there. This is large viz with separated out its legs. And this is our method called PackMap. PackMap is quite a good method. We use it for just about every applied paper we write. And other people are using it too. It's got a bunch of GitHub stars, like 500 or so of them. It's got some nice software awards from the ASA. Just a little bit about the name. It's kind of a stupid name. I mean, PackMap sounds like Pac-Man. I didn't name it. My collaborators chose that name. Anyway, it's a useful algorithm. So do you want to see what it does in the FICO data set? So I was curious. So I asked my student to do this, and she did. And I said, no way, PackMap did that? And she said, yeah, what's wrong with it? I said, come on. I said, no way. PackMap produced Pac-Man on the FICO data set. I said, and there is a technical explanation for this. There's some structural missingness in the data. I mean, it's actually mimicking what we see in our models. But anyway, it's really hard to take this result seriously. Okay, so takeaways: vast number of real-world problems don't benefit from black box models. They do not, they cannot, they never will. I've given you both empirical and theoretical evidence, something like a proof that interpretable models should exist for noisy problems. Regulation is needed to prevent abuse in high-stakes problems because companies like to inflict black box models upon people in high-stakes situations, and interpretable AI is cool. And now for your, I'm going to reward everyone for not asking questions during the talk. But again, please feel free to come up afterward and ask questions. But so this is the Blackwell seminar, and this is about making AI and statistics and machine learning accessible to everyone and wanting everyone to be a part of it. And so a number of years ago, I started writing bluegrass music about machine learning. And so I never get to play them because my favorite person to play with is a professor at the University of Washington, and I never get to see him. But he's here. This is Dargan. Dargan Frierson. And so I'm going to, the first song we're going to sing has never been done in public before, okay, because it requires some harmony, and I'm going to share my screen so that you can see it properly. Okay, I think I might need a little help with the Zoom thing. Oh, screen mirroring, let's see here. Oh, no, it should be fine. Yeah, no, we're good. Okay, great. Okay, so this song, this is a love song to my K-nearest neighbors. So K-nearest neighbors, K-nearest neighbors is a machine learning algorithm that it's a very simple algorithm where you just look at the points that are close to you and you take the majority vote of their labels. Okay, and so this is a love song to my K-nearest neighbors. Okay, so great. So let's give it a try. Okay, ready? When I look around, I'd find you there in space, and I see that you are like me. The future is ours, the oyster, our world, where things far away just don't matter. 'Cause I can count on you, 'cause you know me too well. You just sit right there by my side. In a metric space, we can find our place. For each other, we truly decide. My nearest neighbors, my nearest neighbors. If I were missing a part, you would extend your heart, that I could be whole once again. You're singing the wrong part. Start over here. Ready? If I were missing a part, you would extend your heart, so that I could be whole once again. And when clustering, I'd do anything, so that I would be with you, my friends. My dearest neighbors, my nearest neighbors. And all the K of you with K more than two. Together we work as a team. Case-based reasoning can do anything. Perform as you fathom to dream. My nearest neighbors, my nearest neighbors. 'Cause I can count on you, 'cause you know me too well. You just sit right there by my side. In a metric space, we can find our place. For each other, we truly decide. Cool. Okay, take that away. All right. Okay, so this song is about convexity. And if you're not that familiar with convexity, so the idea with convexity is that, you know, a convex function is one that if it were a valley, right, it would be one valley. And you can see everybody from everywhere in the valley, right? So if you're not convex, it could be like multiple valleys. And in the case of neural networks, it's very hard to optimize because it's not convex. And so anyway, this song is called The Land of 10 Million Valleys. Okay. I was born in one long valley where gradients would shine the way. Like a beacon we would follow, could always find my love this way. Some years ago we left that valley for greener lands that were non-convex. But how to find my love in these lands, I'll never know, I'm so perplexed. I lost my love in the land of 10 million valleys. If only we did never leave the land of convexity. Now I'm alone without my kernels. No QP solver will help me. Just valleys within valleys, the hell of non-convexity. I'm out of time, my gradient's vanished. I'm out of memory. If I can train this neural network, oh, it'll be the end of me. I lost my love in the land of 10 million valleys. If only we did never leave the land of convexity. Thank you, darling. Okay. All right, 3 minutes for questions. Great. Okay, thank you. Does anyone have any questions? We're working on it. We're going to record some. I actually have a whole slew of songs.
Is this the first recording? Because it's recording.
I think for that song, we could do better. We could do better. Yeah. But I wrote a whole slew of songs, so I have one called I Can't Beat Logistic Regression. What are the other ones? Can't remember what the other ones are. The Multi-Arm Bandit. That one has a music video. You can watch that online. I have a love song to what? Regularize. And I have a love song to IID random variables.
All right, any questions? Yeah, we have a question.
Okay.
Kind of, towards the end, you talked about like just introducing like regulations and practice sort of like in society how you would like to see perhaps models being employed or not employed. So what would those regulations look like?
So for high stakes decisions, I would say don't use black box models unless there's no equally accurate interpretable model, right? So I think for some cases, and you have to name specific domains, like for loan decisions, for instance, like why are we using black box models? I mean, I know these guys want to keep their models proprietary, but would it really be so bad if they didn't? Or if they at least gave you a reason that was faithful to your loan application. Criminal justice, I see no reason to use, So I think we need to regulate that. There's a whole other, if I was going to regulate, there's a whole slew of other stuff I would do. I would limit the use of facial recognition to people who had certifications to store facial recognition data. I don't really think facial recognition should proliferate. I think it would cause a lack of privacy, particularly, I mean, you think about people in the witness protection program, oh my gosh, right? They don't want facial recognition propagating. There's certain kind of AI code that should just simply be illegal, right? There's no reason to have like denudifying code. There's no good purpose for that. Voice cloning software that's used for the kidnapping scans. I mean, there are valid like use cases for voice cloning, like for example, if you lose your voice and you want to clone your own voice, fine. But I think you should have to get like a permission to do that. And so, you know, not anyone could clone my voice and whatever. I don't see why anyone has to be able to speak in my voice. Like, I don't think that's okay. I'm working on some regulations now for like, I'm trying to write some, well, not regulations, but like recommendations on improving online safety, individual safety, like bullying, stalking, all that kind of stuff that can get a lot worse with AI. Does that answer your question? Yeah. Okay. Yeah?
But let me push a little bit on the very first statement. And it's not that I disagree, but your interpretable model may be my black box model, right? So some people would argue that a ReLU with 2 levels is interpretable enough. That should be allowed. So how do you operationalize the statement that I definitely agree with?
Yeah, it has to be done per application because interpretability means different things to different applications. And so, you know, I mean, so we wrote a review paper on interpretability a couple of years ago, and that was one of the kind of principles of it that, you know, the definition of it has to be application specific. So for instance, images, interpretability means something completely different, like sparsity in image, like sparsity in pixels is stupid, that's not interpretable. So you really have to define it per domain, and you need a committee to like say, this is what we mean.
So my question was, after hearing about the news of the intrusion, I was a little concerned that maybe companies and governments may not be incentivized to aim for interpretable models and may aim for black box models if they think it will profitable part. So do you get any ideas for how to convince governments and companies to build interpretable models instead?
So regulations is one way to do it because it's a rule and it says this is what the people have decided. You know, the people went to the government and said we need to do this. So that's one way to do it. You know, it also could take like a, you know, if let's say one, well, not criminal justice, because the criminal justice is the worst for that because you've got all these like companies wanting to sell governments black box models. And so, you know, what you need is criminologists saying to them, you don't need to buy that model. You can just use this free one over here that was produced by, you know, the, sorry, what's the name of that? There's a charity that produces free criminal justice models, and they're good. The Arnold Foundation, right? They produce free criminal justice models. We tested them. They were good. So, you know, and then if you want something specialized for your state or something like that, maybe that's something academics can help you with. Do you really need a company to, you really need to outsource that to a company? I'm not really sure. And the companies are just going to do logistic regression anyway. Yeah?
I had a question in regards to converting the rational set. So do you have some kind of guarantees that, let's say the example you used for listening about like 1 million trees within the rational set, is that exhaustive in the sense that those are all the models in the rational set, or do you speculate there are actually more models in the rational set?
Okay, so for tree farms, it gives you all the models in the Rashomon set. It excludes certain trivial models. So for instance, if you could add another split and still stay in the Rashomon set, like just adding a split for no particular reason, like they both vote positive. And so you could just condense those into one that would vote positive. So it wouldn't include the tree that would have the additional useless split. So it's everything in the Rashomon set without these silly trees. The faster risk algorithm produces a sample from the Rashomon set and doesn't produce the whole thing. Yeah, it's because we don't know how to do it yet. Yeah?
Maybe comment on the strategic quantification aspect, like especially like for example for this pipeline that you were describing, where maybe user or decision maker would have some kind of like
So what type of uncertainty quantification do you want to incorporate?
I mean, so like I would imagine that like I understood correct, like at the end of the day, you want to produce some models which will be like do some kind of prediction to support decision making, right?
Mhm.
I guess either you maybe like to have some kind of uncertainty quantification.
So the whole Rashomon set is uncertainty quantification because you're like enumerating all of the models that could be used. So that's more than a regular machine learning algorithm, which just produces one model. But you could take any model and do anything. You could produce uncertainty bands for what it depends on the model class, right? So for decision trees within each leaf, you can get the number of positives and the number of negatives. So you can produce confidence intervals based on the binomial distribution. You can always do bootstrap confidence intervals if you want to on any of these things. I just don't know what kind of uncertainty you're talking about.
Yeah, I think it more or less answered the question. So like I was just thinking that like, if this is correct, you want to use kind of like procedure to either judge or prediction, and that they would use kind of models coming out of the pipeline to do some kind of decision making, and yeah, you would like to know some kind of like assertive classification around the predictions.
Yeah. Okay. So maybe I did answer it then. Yeah. Okay. Thank you. Yeah.
Ask a quick question about the theoretical result. So in terms of like this ratio of the overall, the Rashomon set for the overall, so the Rashomon set is defined with respect to the particular class of models you're fitting. So that result by itself is maybe kind of could be misleading, right? Because it's not like the best model in the larger model class could be a lot better than the best model in the simpler model class, right? Because epsilon is with respect to the specific model class you're searching over.
Yeah, it's like 5% above the best or something like that. Some
Yeah, but that's
epsilon above.
within the class of mod, so that this epsilon is defined with respect to the model class you're searching over.
Yeah. So the
If I go from linear to something else, could be completely different objects.
well, okay. Okay. I'm a little confused. If you're working with trees, right, then the smaller model class are just smaller trees, and the bigger model class are bigger trees. And then if you're working with like linear models, you can have sparser linear models and less sparse linear models, or GAMs, right?
Yes, but the reference point is the best model in the given class, right?
It would be within the bigger class.
Oh, it's within the bigger class.
Yeah.
Oh, I see. So I misunderstood. So
Maybe I didn't explain it.
No. Okay, so it's all with respect to the bigger class. That's the reference point.
Yeah,
I see.
we can go and check it later, but I'm pretty sure it's within the bigger class because the way we set the whole thing up was like, there's a big class, then there's a Rashomon set in it, and then that Rashomon set has a ball in it, and then that set is covered by. Okay.
I just think I spaced out.
I'm sure you didn't space out. That was a very, very good question. Okay, cool. Yeah.
I'm wondering about your very elegant proof about noise. If, like, I don't know how the logic necessarily works. Could you show that, like, if there are good simple models for a given data set, then there's noise in the data set, or if there are good simple noise?
I don't think so. So you could have the situation where like the positives are over here and the negatives are over here, and there's a ton of good models. So you can have a really large Rashomon set with a really super clean data set. So that would contradict. It would contradict your hypothesis. But you can tell how much noise is in the data set pretty easily by running boosted decision trees. Right? If you run boosted decision trees, you'll get some accuracy on it, and then you'll know how much noise is in the data set anyway. Yeah. Okay, I think probably okay.
Yeah, I think like we have a time.
Okay.
So let's send our speaker.
Cool. All right, and I'm happy to stay and answer questions if you want.